Topic of this week, if you weren't already aware, is going to be all about alternative consensus mechanisms. So these are ways to achieve what proof of work does, which is achieving consensus, without necessarily doing it the way that proof of work likes to do it. So we're going to go over a few different topics. First, we'll introduce distributed systems, what they are in general, so that you have a better idea of what needs to happen in a distributed system. We'll then go over proofs of something else, which are proof of work-like algorithms that they expend some resource to cast a vote. We'll go over proof of stake a little more, talking about the particular implementations that are popular. Then Rustie will continue with voting-based consensus algorithms and federated consensus. All right. So first, distributed systems. The question is, what does it mean when you talk about a distributed system? The definition varies from person to person, but the consensus between people is that it involves a network of independent nodes, each representing some process which talk to each other via messages. So in the system, every node is its own process, meaning that it does its own computations, it does its own activities, and it shares information between these other processes via messages. And the properties of distributed systems, as you can imagine, are that you have concurrent components. Things are working side by side. They're not necessarily working one at a time because you have things that are not relying on each other. You have message sharing, which means that if you have dropped messages or an inability to send messages, then you'll have partitions. You have no global clock, meaning that you can't rely on time, which means that you want to ensure, for the most part, that you have an asynchronous environment so that you don't have to rely on any one process's message or any one process's completion of some computation. And you can expect that there's going to be failures of some individual components of a distributed system. That's inevitable with any machine. That one machine might fail. The thing you want to keep in mind is that you never want the system to go down because one machine has failed. So there's two ways to prove the correctness of a distributed system. That's by proving that it satisfies two different properties. These properties are safety and liveness. Safety properties are what a system should never do, and liveness properties are what a system should do. So it's natural. You say what something should do and what it shouldn't do. Here's why you want to make sure that something always has safety, because let's say that something is completely live. That means it's always doing something. If it's always returning some value, it's meaningless if it returns every value that appears, which could include incorrect values. Right? So having a system that's only dedicated to liveness is a trivial system and meaningless. So if you go to the other extreme, where you have only safety, the system never returns any false value. You say it never returns any value at all. We satisfy safety, but now it doesn't tell us any information about the system, which means that it's meaningless as well. It's trivial. So the key is finding a way to balance these two properties such that you can achieve one while also not sacrificing the other. And every distributed system needs to come to consensus on the values that it stores. Right? So the correctness of a distributed system is achieving its intended goal, which in our case is coming to consensus on some log of information. To ensure correctness, one uses a consensus algorithm to achieve all three of these following things: validity, agreement, and termination. In other words, when these nodes come to consensus, they need to come to consensus on a valid value, meaning a value that's proposed by one of the processes. They need to all come to consensus on this value. If they come to consensus on a value, all the non-faulty processes have to come to consensus on the same value, meaning that you shouldn't have one set of nodes come to agreement on one value, another on another value, because then you have a lack of consensus in the system, which is not achieving the intended goal. You see that agreement is a safety property because it means that this bad thing will never happen, that honest nodes will never decide on different values. Keep in mind we're focusing on non-faulty nodes or on honest nodes because we don't care what faulty nodes do as long as it doesn't interrupt the consensus process. If a faulty node chooses to always disagree with the honest nodes, it's fine. It can do that as long as we can recognize what the honest values are. And finally, termination, which means that all non-faulty nodes will eventually decide on some value. And this is a liveness property. We want nodes to eventually decide on some value because if they never decide on a value, yes, they satisfy the safety property of never coming to consensus on different values, but then they never come to agreement on any value. And that is a huge issue, because then we can't do anything with our system. All right, any questions so far? All right. So the CAP theorem is a fundamental theorem for any distributed system, which talks about what a distributed system is able to achieve. There's these three categories of things that one can achieve with a distributed system, but not necessarily simultaneously. Consistency is the idea that every node provides the most recent state. So if one node is updated with some value, then when a node returns a value, it should return either that value or a more up-to-date value. Availability is that every node has constant read and write access. That you can always give it information and you can always receive information. And partition tolerance is that the system works despite partitions in the network, where a partition is dropped messages between nodes, essentially where nodes cannot communicate. So you can only have 2 out of 3 of these at any given point. You see this small intersection? That's what we call a magical fantasy land, because there's no way to achieve all 3 of those at the same time. You might hear about some distributed systems claiming that they can achieve consistency, availability, and no failures at all. That's a lie. There's no way to achieve all 3 of those at the same time. And it's pretty straightforward to see why. So let's say that we have partition tolerance and availability. This means that we're not going to be able to be consistent. If I tell node 1 that my favorite color is red, it'll try to tell every other node that my favorite color is red. It tells node 3, tries to tell node 2, tries to tell node 4, but it can't because of this partition. So when I ask node 2, and I want the system to be available, what is it going to do? It's going to return to me the most up-to-date value it has, which is blue, my favorite color from 4th grade. But that's not consistent with what I told node 1, meaning that we don't have consistency. So, okay, we're going to swap out consistency or availability for consistency. But now we can't have availability, because if I tell node 1 that my favorite color is red, and then I ask node 2 is either going to return an error or return nothing. It won't be able to give me a value because it doesn't have the most up-to-date one, meaning that it's not returning an older value, but it's not returning a value at all. So it's not available. So we have consistency and availability. This is why we can't have partition tolerance. This is why we can't have nice things. So I tell node 1 my favorite color is red. Node 2 tells me my favorite color is red because node 1 was able to tell node 2 the updates. But if we can't put a partition here because then the system's not going to work. In real life, you can't expect systems not to be partition tolerant, because if you have a system that's not partition tolerant, then even a single failure could disrupt the entire system. So we always want to make the assumption, or we always want to make sure that we're able to achieve partition tolerance, and then from there decide between consistency and availability about which one we prefer. Yeah, question?
In the second case, where it returns nothing or an error value, how would it know that it doesn't know the most up-to-date value is partitioned off?
Right, so that's a good question. How does this know that it does not have the most up-to-date value? You might have the node query every other node first and wait for a response from all other nodes before it returns a value. So if it never gets the, if that makes sense. All right.
Well,
yeah, go ahead. Okay. All right, any other questions? Sweet. All right, then the Byzantine generals problem. How many people have heard of this Byzantine general problem or are familiar with it? Okay. All right, that's a good amount. The Byzantine generals problem is a classic problem involving traders in this group of Byzantine generals. Imagine you have a bunch of different generals who are deciding whether or not to attack a city. They have to either all attack or all retreat. If only part of them attack or only part of them retreat, then their forces are going to die off. If there are some dishonest nodes, we don't care about what they do as long as we have all the honest ones choosing on the same thing to do. So the issue with this is that the city is wealthy, and the city is able to bribe these different generals. So what happens if the city bribes a general to lie to their peers? Well, you notice that if we have just 3 generals, there's no way to come to consensus on what the correct value is. There's no way for the honest nodes to agree on what the decision actually is. If we have the commander and lieutenant who are both honest, but Lieutenant 2 was bribed with 100 Bitcoin, then you're going to see that Lieutenant 2 has the ability to lie to Lieutenant 1 and make Lieutenant 1 not able to discern between what the honest value is and what the dishonest value is. If the commander tells both Lieutenant 1 and Lieutenant 2 to attack, But Lieutenant 2 says, oh, the commander said to retreat. Now Lieutenant 1 sees two different conflicting responses. He sees attack from one and retreat from the other, where they should be the same value. If we look at the second example, where the commander is the one who was bribed, he tells Lieutenant 1 to attack, Lieutenant 2 to retreat. Lieutenant 2 dutifully responds to Lieutenant 1 with what he heard from the commander. To Lieutenant 1, it looks the same. It looks exactly the same as it does in the first circumstance, meaning that it's impossible for Lieutenant 1 to tell who the liar was between these two circumstances. So, because of this, there's no way to solve for more 1/3 or greater Byzantine faults. There was a solution, a paper released in 1999 by Miguel Castro and Barbara Liskov, which was the practical Byzantine fault-tolerant algorithm, which assumes complete asynchrony and allows for up to 1/3 faulty processes. And this is like the foundation for a lot of different upcoming algorithms, such as the ones that you'll see in further in the lecture. There's two types of faults that we discussed. This one particularly considers the type of faults where you have Byzantine faults. We discussed fail-stop faults, which are nodes crashing, not returning values. You can detect these faults because nodes can say, hey, are you still alive? And he doesn't respond. That means he's dead, right? So that's easy to detect. But a Byzantine fault is more difficult to detect when nodes can send incorrect or corrupted values as well. And they can manipulate people either intentionally or unintentionally. And that's much harder to detect for obvious reasons, because you can't necessarily discern without a large enough group of honest nodes who the liar is. All right. Are there any questions about any of the things in this section? All right, sweet. So now we're going to talk about proof of something else. These are all of the different algorithms that have been proposed that are alternatives to proof of work, which are Nakamoto consensus based, where you expend some resource to cast a vote. So proof of stake is one of the popular proof of something else's. This picture doesn't have anything to do with proof of stake. I just thought it was kind of cute. So proof of stake, a quick review. You have validators instead of miners. You have people who vote on blocks instead of computing some hash puzzle, and they lock up stake in order to gain voting power. And the resource consumed here is going to be the native currency. So Ethereum, which plans to launch proof of stake Casper, is going to require anyone who wants to vote in eventually. In the pure proof of stake version, they have to have some ether invested or bonded rather that they would use to get a higher chance of being able to vote. Right. A hybrid between proof of work and proof of stake is known as proof of activity, in which there's a two-phase process, the proof of work phase and the proof of stake phase. The idea was to combine the value of the two algorithms. So in the proof of work stage, you have miners that are solving and submitting block headers and propagating these to the system. These may or may not contain transactions depending on the implementation. And then after a certain period of time, you will now move to a proof of stake round in which validators will vote on valid blocks and will receive awards for signing on blocks that eventually make their way into the converging chain. So in here, you're consuming two types of resources. You're consuming the resources of proof of work, the electricity, the hardware, the cooling power, and proof of stake resources, which is the native currency. Some people say that this is unnecessary, that you're now spending more resources than necessary when proof of work by itself works, or proof of stake by itself may work. So the question is whether you need all of these different components. I think these images are pretty amusing. They're all buzzwordy. CPU efficient, energy efficient, amazing security, maximum decentralization. But it's in the space, it's pretty easy to pick out which types of things are and are not legit. You have proof of burn, which is like proof of stake, but a little bit edgier. So instead of locking up capital, you burn it, meaning that you send it to a place where you can never retrieve it. So if you're familiar with proof of burn from the scripting lecture 3, you send some coins to some address from which you cannot retrieve it, like 1-800, I don't care. So in proof of burn, you burn some coins to be given a chance to vote or propose some block in the next voting round. You can also use proof of burn as a bootstrapping mechanism. You tie your coin's value to some other coin. You say, okay, if you want to burn 0.01 Bitcoin, you'll get 100 whatever coin in my system. Right? So by that, you're saying that the exchange rate from this to that is exactly this much because you're proving people are willing to burn this much coin to get this much reward. So the resources consumed are some currency. It doesn't necessarily have to be the native currency. It's any currency that you can prove that you can send to some irretrievable address. People complain about this one because now you're taking a bunch of currency and wasting it. Right? You can't get it back. It's lost from the supply forever. There's this idea of proof of space, which uses a different type of resource. Instead of using some currency, it uses memory or space instead. The challenge is to, or rather, use disk space to solve some challenge. So if someone requests from you this piece of information, then the puzzle is such that you have to have a lot of memory stored in order to respond to what the answer is to that question, to that challenge. Nowadays, people use this proof of space idea for file storage. There's SIA, Filecoin storage, which all attempt to do the same thing, decentralize the way, or just make a decentralized cloud where you can stick stuff in this decentralized network and have proof that someone actually owns your file without having to own the file yourself. I mean, there's no point in having someone store your file if you have to store it as well. So there's two variations of implementations that are popular. One is letting users receive coins after voting on blocks, like proof of capacity, where you prove that you stored some information and then you can get rid of it after you finish voting. But there's also the one in which you store information in the long period in order to get some rewards, such as Filecoin and all the ones that I mentioned here. So the resource you consume is memory. And the complement of space is going to be time. So instead of consuming space, you consume time instead. Keep in mind that the whole point of proof of work is to randomize the selection process based on how many resources you have. So even if you have only 1% of the hash power, you still expect to get 1% of the blocks in some given time period. But why waste all this energy on hashing when all you want to do is randomize who gets what, depending on how many machines they have? So this is what proof of elapsed time aims to do. How many of you guys have heard of trusted execution environments before? All right, so a quick overview on trusted execution environments. Those are environments in which you have some outer operating system, which is meant just as a way of letting the inner operating system run on its own. This inner operating system cannot be touched by the outer machinery, meaning that if, for example, in your phone you have a fingerprint sensor or reader, this is usually, at least in Samsung phones, run through a trusted execution environment. That's why when you start up your phone, you're not allowed to put in your fingerprints. You have to have the first put in your PIN, and then from then on you can use that fingerprint sensor. It's not able to be accessed by the outside environments, meaning that everything that happens inside this trusted execution environment is trusted to execute properly, or if it doesn't execute properly, will not be able to tell you that it did. So every time that one of these is run, you can ask for an attestation that it ran the code correctly, and only if it provides that attestation will you trust the results of that operation. And the reason that this is useful is because you can use these trusted execution environments to do anything you want to provide an attestation and trust that something will run correctly, like running a timer, for example. So there's these Intel SGXs, which are trusted execution environments for general purpose things. Let's say that you want to store some, you ask your SGX to wait some amount of time. You ask it to run a timer for some random amount of time decided upon by the SGX. So you don't tell it to wait for 5 minutes, 10 minutes, 15 minutes. You say wait for some time based on this random function. It'll spit out a number based on whatever random function you have, which will probably be like on average 10 minutes, but it may say, oh, you got lucky, you got 9 minutes of wait time, or oh, sucks for you, it's 30 minutes of wait time. Everyone will send those requests to their SGXs, and whoever gets lucky enough that they now have and they have a shorter wait time, once their SGX has waited that amount of time, has run that timer, then it'll provide an attestation. Yes, I ran this timer correctly for this many minutes. So the first person who's able to complete this random wait time, let that person be the one who gets to choose the next block. So now you're tying people to these machines without forcing them to spend energy to prove that they are tied to those machines. However, you do make an assumption that that Intel is producing these SGXs properly. It's interesting because we make these assumptions on a daily basis about our phones, about our laptops. We assume that our machinery there's no backdoor, that no one can see our information or what we're doing. So the arguments that it's an interesting argument as to whether or not SGXs that are produced by Intel should be trusted. And the resource consumed here is time. So are there any questions about, yeah, go ahead.
So what is SGX and Intel SGX?
Right, so an Intel SGX is a particular trusted execution environment that, it's like an implementation of it where you can use it for general purpose things.
So it's a software or is it a hardware?
Hardware, yeah. It's a physical device that will run things without being able to, will run things without the interference of any outside operating system. There's an interior operating system that runs things without any information being detected by the outside. You can send something encrypted in, it'll unencrypt it with its personal private key, run some operation, then re-encrypt it before it goes out. So the outside operating system sees nothing or can make no sense about what's going on inside. Yeah. Any other questions? All right. And then a quick recap on proof of stake. So there's a couple popular implementations. These are the ones that we chose to talk about. There's Tendermint and there's Casper. Tendermint is mostly asynchronous. It's a BFT consensus protocol where voting power is denominated in validator stake, the same way that you've heard proof of stake from the last lecture. This is a two-stage voting process, and Tendermint actually favors safety or consistency over availability. This is what was designed to be used for the blockchain network Cosmos. And then you have Casper, which is Ethereum's soon-to-be-released Nakamoto or BFT hybrid proof of stake algorithm, which favors liveness or availability over safety and consistency. This is like Casper the friendly ghost. So this is what proof of stake looks like in Tendermint. You have these three different significant checkpoints at which you'll decide whether or not something's valid. So you start off always at a new height, and from there you will propose a new block. And someone will be randomly chosen to propose the block based on the amount of stake that they have in the system. And everyone else, this is the only synchronous part of the entire consensus protocol, means the only part of the consensus protocol in which you expect something to happen in some particular time. So you say, okay, within the next minute after the last round, or the last block was confirmed, we want to see a new proposed block, else we're going to move on to someone else. So someone proposes a block, and if you see that block and it's valid, you'll say, hey, this is a valid block. Otherwise, if it's not received in time or it's an invalid block, you'll pre-vote nil. Then you wait for 2/3 pre-votes from the entire network, right? The 2/3 being because of the Byzantine general problem, you can only tolerate up to 1/3 of faults. So you don't want to confirm a block unless you know that you have 2/3 or more people behind it, meaning that you can't make a faulty decision. And this is what's referred to as the polka. So you don't actually need any dancing experience for this. This is just a fancy term that they used to describe the 2/3 voting process. And once you have seen 2/3 pre-votes, which could be in either way, then you're going to pre-commit to the block either nil or pre-commit for the block, depending on how many pre-votes you saw for the block. Then you wait for 2/3 pre-commits again, and if you see 2/3 pre-commits, you'll commit the block to your blockchain, else you move on to a new round. So this favors consistency over availability, because with just over 1/3 of the total voting power, you can stop the consensus protocol. But it would take more than 2/3 to actually commit something that is invalid. Right, so this makes it energy efficient and fast, because you're not mining anything, you're just limited by the rate at which nodes can connect to each other. And this is what makes it excellent for enterprise blockchains. You have a preset number of validators who have stake in the system, and you trust on them to be always connected, or at least very often connected. And you can still tolerate up to 1/3 faults in this Byzantine vaults in the system. Are there any questions about Tendermint? Then Casper. This is a chain/BFT style hybrid, at least in the beginning, where you start off with both proof of work and proof of stake. The idea is that if you make decisions that are going to lead to a converging chain, then you make money. And if you don't do that, if you make decisions that lead to a diverging chain, then you're going to lose money. Anyone can bond tokens in the system. Unlike Tendermint, you're not limited to a certain validator set. Anyone's able to become part of the validating process. So yeah, Casper is all about a more free version of this, in that anyone can be a validator, anyone can be part of the consensus process by locking up the stake independently. It will be initially proof of work, proof of stake hybrid before transitioning slowly into proof of stake purely. The way this works, proof of stake or proof of work as usual will continue, but every 100 blocks or so you'll have a checkpoint, at which point proof of stake validators will say, all right, I think that this chain of the last 100 blocks since the last checkpoint has been valid. I will commit to this block as a checkpoint saying that that this block can never be reversed. This chain can never be reversed. So even if 99% of all the voting power tries to revert it later, the users will refuse to go back on that checkpoint because at one point all the validators had said that they see this checkpoint as valid. So that's what will allow people not to go back on their word, even if they try to vote against it later. And then slowly it'll transition into proof of work such that you only have voting on blocks. Any questions? All right, sweet. Now Russ is going to go into voting-based consensus algorithms.
All right, so actually let's take a break first and explore some pretty pictures I found in Google Images. It's a Greek island off the west coast of Greece. Yeah, pretty pretty. The island's name is Paxos. What you guys might not know is, there's another picture. You might not know is Paxos is in fact a Greek island, but it's also consensus algorithm. All right, yeah. So Paxos was invented in 1989 by a guy named Leslie Lamport, who's like a god of distributed systems. I think Nadir mentioned him at some point. But yeah, published Paxos in 1989 was a really elegant solution for like consensus algorithms, but like the story is he had a hard time explaining it, so he had to come up with this story of like how the government on the island of Paxos has to use this consensus algorithm to come to consensus on like the new laws and bills they pass. Right, so on the island of Paxos, there are 3 different types of people in the government. They're the proposers, acceptors, and learners. Proposers, in like distributed systems talk, they advocate for the client request. The client talks to the proposer, and then the proposer, like quote unquote, makes a new bill and sends that message to the acceptors, who vote on the bill, right? And then after the acceptors talk amongst themselves, send some data back and forth between the proposers and themselves, they send the final result to the learner, right? This is after consensus has been reached. The learner will save the info and return it back to the client. And that's how you like store information. So key terminology we use in Paxos, a quorum is any majority of acceptors. And we define quorums in such a way that any 2 quorums must overlap. So informally you'd say that any 2 quorums must share at least one member, so they overlap. Right. Main idea of Paxos is that we want to come to consensus on one value. Paxos only works for one value. We'll see later on how we can layer different instances of Paxos on top of each other to make what's called multi-Paxos. But Paxos is only for one value. The protocol proceeds over several rounds, and each round has 2 phases. And after everything, we come to consensus on a value. Data flow is that the client will talk to Paxos, and then within Paxos, like little Paxos government, will talk amongst themselves, come to consensus, pass ballots, and then at the very end, the learner, which saves the data, will send it back to the client, and that's how you process a query. All right, so the first phase in Paxos is called prepare. And so after the client talks to the proposer is like, all right, we got to query some new information. They'll create a new proposal n being like some sort of index number. And we define the index number as like a number that we increment for every proposal, right? The idea behind this is that we want to keep some sort of sequence of proposals, right? We never want to look back and accept a proposal n-1 when we know we're already on proposal n. We'll see that later on in step 2. But a proposer creates a proposal n and sends it to a quorum of acceptors. Kind of looks like that. So the proposer asks the acceptors in the proposal, right? Like, what's Rustie's favorite color? And here I have the index number 10/24/2017, because that's today's date. And it sends it to a quorum of acceptors, so there's 3. And after the acceptors get this proposal, they have to make a promise. And the promise is kind of what I alluded to before. They can't accept a proposal that's like outdated. Like if they've seen a proposal n+1, they can't accept proposal n, right? You never want to go backwards. So if an acceptor has seen a proposal n+1 before, then they'll just send that value back along with their promise. Otherwise, they'll say like, hey, we've never seen anything past the proposal n, and like therefore send no value back. But then it's still like they still have to send a promise back. So that kind of looks like this. Acceptors can either be like, wait, I don't know Rustie's favorite color, please help. Or they could say, yo, it's blue. And this gets sent all the way back to the proposer in a promise. And after which we enter phase 2, and the proposer sets a value to their proposal. And this value is either the value sent back by the acceptors based on like the previous proposal they've seen before, n+1 value, or if the proposer gets no value back from the acceptors, the proposer will just like add a value to the proposal depending on the user query. And then after that's all done, the proposer will send it back to the acceptors. Right? So the proposer is like, okay, Rustie's favorite color is blue. And after all that's said and done, the acceptors will again check if the proposal has like not been seen in the past before, and then they'll accept the value and send it to everyone else in the network, including the proposer and also the learner. So here you can see the learner like learns the value that we've come to consensus on, and the acceptor is like, hey, right, Rustie's favorite color is blue. Please confirm. Like, everyone remember this. After which point the learner can return this value back to the client. So some assumptions we have to make about Paxos is that Paxos only works in a fail-stop situation, right? Nadir talked earlier about the difference between Byzantine faults and fail-stop. So Paxos kind of only works when you make certain assumptions about how much you can trust the nodes within the system. Right, so no Byzantine failures, the nodes can't act arbitrarily, and the way Paxos kind of mitigates this is by saying that nodes that fail at any point inside the consensus algorithm won't affect the entire network. So an example of this would be like the consensus algorithm will never get stuck if acceptors fail to return back the value for proposal n. The proposer is going to be like, hey, what the heck, I didn't get anything back. And then because they get nothing, they'll just launch another proposal, or they'll submit another ballot, n+1, yeah. And tying this back to what Nadir said earlier about safety and liveness properties, some properties about Paxos is that learners can only learn values that have been proposed or submitted into Paxos. Fairly straightforward. If there is a proposal, a learner will eventually learn some value, so that's kind of like termination, right? And also, at most, one value can be learned. Two learners can't really learn like two different values. And Paxos in practice, we kind of mentioned earlier that Paxos, because it only works in a fail-stop environment, we can't deploy it in like some like huge open networks. So we kind of have to like make it permissioned. And that's great for like enterprise systems, right? Like Google uses Paxos in their log servers. Imagine like the huge Google data centers. If one of them fails, right, how do we recover the data? And use Paxos. And that's what they do. So yeah, Paxos is pretty fast, but only in fail-stop situations. Paxos, yeah, only works for coming to consensus on a single value. There is multi-Paxos, but historically it's been hard to understand or hard to implement. Like the person who wrote the paper made it really hard to understand or something. But yeah, anyways, there's a better alternative called Raft. It's easier to implement and also used in JP Morgan's Quorum, which is a Raft-based consensus. And the joke is that Raft is like the raft you use to sail away from the island of Paxos. Yeah. All right, delegated proof of stake. We mentioned earlier that like proof of stake, you stake your tokens, and then based on that have a proportionally higher chance of like getting to propose the next block. The problem with that though is that the more token you have, the more you can stake, right? And that kind of like converges into like centralization if you think that the richer people who own more tokens will always propose them, stake them, and then like be able to get the block rewards, right? So the picture I got from Cointelegraph, and the quote that came along with it was that in proof of stake, the rich get gradually richer. One way you can mitigate this is by implementing delegated proof of stake. The point of delegated proof of stake is that you would essentially invest your token into delegates who would vote on your behalf. All right, so if you yourself don't have that much token, but you delegate to someone else who would also be accepting token from other people, and you like amass all those tokens together, you would have a proportionally higher chance of having a voice in the network. Yeah, so basically you invest in delegate nodes, and delegates will help you secure the network. Delegated proof of stake was first implemented by a company called BitShares in 2014. They're a decentralized exchange platform, and the way it works is that their digital assets have internally are backed by an internal core currency called BTS. Right, federated consensus. So the idea behind federated consensus is that kind of like what we mentioned earlier with Raft in the concept of quorums, except that, well, not Raft, Paxos. But the way Paxos works is that you'd have to predefine what the quorums are, but that's kind of centralized because you have to rely on a central entity to determine that. So a federated Byzantine agreement is the idea that you'd have individual nodes determine who they trust or the quorums that are associated with. And this could be determined by an external criteria. For example, if there's a bank within the network and the banks have like a incentive not to fail, so then you could add them to your quorum. Right, so quorums are, as we said earlier, they're like a majority of the nodes in the network. They're a set of nodes sufficient to reach agreement. And we also define another terminology called a quorum slice, which is a subset of a quorum that can be used to convince one particular node of agreement. So in the picture below, there are 4 nodes in a quorum, and 3 of them are in a quorum slice. So the idea is that we want to pick quorums and quorum slices in such a way that they intersect as much as possible. We can kind of like see why this is by looking at the opposite, where they are disjoint quorums. If there are disjoint quorums, none of them overlap, then there's the potential that 2 quorums agree on different values, and that's no good, right? That undermines the entire purpose of consensus algorithms. So we want to mitigate, like not have this as much as possible. And the way we do this is by like trusting nodes that they will pick, number 1, slices that are large enough to like, by expectation, we'll have quorums that overlap. And also pick slices, or pick nodes to include in their slices that want to maintain their reputation. So you might want to consider adding a company or a bank that has the incentive not to lower their reputation by acting in a malicious manner. And some properties of federated Byzantine agreement. There's decentralized control, again, because we let nodes themselves pick their slices. There's low latency. In fact, we'll see later on that some federated Byzantine agreement algorithms can come to consensus in like 5 to 10 seconds. And there's also flexible trust, because again, we let nodes decide who they consider they can trust, who they like add to their own quorums. So Ripple is a company that uses federated Byzantine agreement. They have their Ripple consensus protocol, and what Ripple does is basically, it's like a cross-border payment system and the focus is on big financial institutions, right? So they'll invite banks to come onto their platform, they'll plug them into the Ripple system, and then through like the Ripple system, the banks can trade amongst themselves using the internal currency. Yeah, that's a graph. And also there's Stellar. Stellar is actually a branch, or not a branch, what is it called? A fork of Ripple back in 2014, but since then they've developed their own consensus protocol. Their focus is slightly different. They are an open ledger, whereas Ripple is a permission ledger. Stellar's focus is more on like the non-profit distribution of wealth, whereas Ripple just like targets banks mostly. So anyone can join Stellar because they are open ledger, and the idea is still the same. Like you get to pick your own quorums, your quorum slices, and that's how you come to consensus. Yeah. And on the Stellar website, they have a pretty cute comic book on like how it works. I recommend everyone go read it. Yeah, they like define all their key terminology, and it's all really cute. And let me check the time. All right, well, there's 2 minutes left. Yeah, let me go to some like extra stuff. So I was doing my research yesterday for this class, because like make the slides the day before, of course. So it turns out that you like pretty much need fault tolerance in like aircraft, say, because like it's like pretty mission critical that your airplane must fly according to plan, right? Like, and in fact, Byzantine fault tolerance was pioneered by like avionics companies, right? So I did research on Boeing 777. They use a consensus mechanism called the Safe Bus Network, and idea is kind of the same as like with all Byzantine failure, Byzantine like fault tolerance. For every node, in this case, they're like sensors or onboard computers. They'll have what are called transmitters. They'll transmit a lot of duplicate data everywhere. And in the case that a computer does fail or a node does fail, then the transmitters that like control these computers can just shut it down. So you don't want a computer on a like mission critical. There's like 500 passengers on board. You don't want it to fail, right? So that's the idea behind it. Same idea with SpaceX Dragon. All right, they launched these $1 million like missions to the International Space Station. So of course they want to have some like Byzantine fault tolerance. They have the Dragon Consensus Protocol required by NASA. NASA required SpaceX to develop their own consensus protocol because like the International Space Station is so expensive, right? They don't want to mess anything up. All right, so they use triply redundant computers, and the actual protocol itself is like proprietary, so like we don't know much about it. Well, at least from Googling, I don't. But like this is more important than like airplanes, because like, you imagine you like launch a spacecraft up like, and then like there's like a gamma ray radiation or something, and like suddenly a bit flips and your computer breaks, right? It's horrible. All right, so Byzantine fault tolerance, and that's how you make sure spacecraft and airplanes operate safely. Yeah, okay, those are the readings for this week. We actually forgot to post the readings last week, so these are like kind of overlap between this week's and last week's material. There's also the comic book I mentioned earlier about Stellar. We'll post this in like the updated lecture slides as well. But yeah, thank you all for coming. If you have any questions, feel free to come up.